Hi folks, we're going to take a look at question 2 from the related rates sheet. Okay, so let's read the question. It says a police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving east. Okay, so let's draw out the scenario. So let's say this represents our corner. Okay, so we have the police car that's moving toward the corner from the north. Okay, and then you have the car which has just turned the corner. So let these represent the distances that they're traveling. Okay, and let's see what's happening here. It says when the cruiser is 0.6 k north of the intersection. Okay, so 6 kilometers north. The car is 0.8 kilometers east of the intersection. The police determines that the distance between them and the car is increasing at 40 kilometers per hour. Okay, if the cruiser is moving 80 kilometers per hour at that moment, what is the speed of the car? Okay, so let's add to our diagram here. Now the first thing that I want to make sure I don't do is put these numbers in my diagram, okay? Because these distances are changing, okay? Eventually I'm going to determine a derivative at this particular moment. But these distances, distance of the car from the intersection and the distance of the police cruiser from the intersection, they're changing quantities. So I'm going to keep them as variables. Okay, so here this will be the distance from of the police car to the intersection. This will be the distance of the intersection to the speeding car. Okay, so I'll call this x and this y. Just go with horizontal and vertical. Okay, and what we're given in terms of information is the speed at which the distance between them is changing. Okay, so since I don't want to use lowercase d, since I can use that for derivative, I'll call this capital D. Now, the reason why I'm working with distances and not speeds is because I'm noticing a right angle triangle. And of course, with a right angle triangle, I can use Pythagoras. Okay, and Pythagoras uses measures of distance. Okay, but the speeds are just going to be given by the derivatives of these quantities. Okay, so let's write an equation to connect these things here. So of course we've got Pythagoras, we've got d squared equals x squared plus y squared. And let's see what information we're given. Okay, so we're given that the distance between them, so this capital D, is changing at a rate of 40 kilometers an hour. So that means that distance with respect to time is equal to 40 kilometers per hour. Okay, and they're telling that the police cruiser is moving at 80 kilometers an hour, but the distance that I'm measuring is this y value. So this is where you have to be careful, because as the police cruiser is moving toward the intersection, this y value is actually getting smaller. So when we indicate its derivative with respect to time, it needs to be negative 80 kilometers per hour. Okay, so make sure that you're recognizing when a quantity is decreasing that you have to use a negative in the derivative to indicate that. Okay, so in the previous section when we were doing implicit differentiation, before we were doing implicit differentiation, we would have solved for d here and had, d equals square root of x squared plus y squared. But now that we have this idea of implicit differentiation, I'm actually going to leave the equation in this form, and I'm going to take the derivative of both sides, okay, with the equation given implicitly. Okay, so let's take the derivative here. So this is d squared, but it's with respect to t, so we're going to have to use a chain rule. So first, the derivative of d squared with respect to d is 2d, okay, times the derivative of d with respect to t. Okay, and I'm going to do the exact same thing with these two expressions. So x changes with respect to time, y changes with respect to time, so I need to use the chain rule in order to determine these derivatives. So this is going to be 2x. Okay, now be careful, we're taking the derivative with respect to time, not with respect to x. So it's going to be 2x dx dt, and here plus 2y dy dt. Okay, and now let's input all the information that we have. Okay, so we have the ddt, which is the d dt, tough to say, which is 40. Okay, we have the x value at the moment in question, tells us that the car is 0.8 kilometers away. Okay, dx dt, well, that's what I'm looking for, is the speed of that car, so that's going to remain my unknown. Okay, plus 2y, we know the police cruiser is 0.6 kilometers away, and dy dt, that's the speed of the police cruiser, or it's the speed at which this distance is changing, so that's my negative 80. And you'll notice here that I don't have the distance between them at that moment. Okay, but this is just a right angle triangle, so I can calculate that. So I need to calculate the distance at the moment where the police cruiser is 0.6 kilometers away and the car is 0.8 kilometers away, and I need to calculate this distance. So d is equal to square root of 0.6 squared plus 0.8 squared. Okay, and you might recognize this as a 6, 8, 10 triangle. So put that in your calculator. I feel pretty certain that this is just equal to 1. So here I've got 2 times 1. Okay, so we see that while we were given enough information to solve the problem, we needed to do a little bit of work. Okay, so let's clean this up here. So we've got 80 equals 1.6 dx dt, and this is going to end up being minus. Okay, and I think here I'll use my calculator. So 2 times 0.6 times 80. Okay, 96. So minus 96. So here dx dt. Oops, dx dt. Let's calculate that. So here that 96 will come to the other side. So 96 plus 80 is equal to 176 divided by 1.6. Okay, and we get 110. Okay, and here the units, since this is a speed, it's how this distance is changing with respect to time. This is kilometers per hour. Okay, and so that's how fast this car is moving at that point. So if the speed limit's 100, this car is getting a ticket. If the speed limit's 120, this car is okay. Okay, that's it for this one.